Chemistry, we're going to start a new unit now, Unit 3. It's called Intermolecular Forces, and this deals with the subject of how molecules interact with each other. So we're going to start off studying gases. So gases are simply detached molecules, molecules that are not connected to each other. Air, for example, is a gas made of nitrogen and oxygen molecules that are separated from each other. They may collide with each other, but they're not stuck together. So if the kinetic energy, that is the motion energy, overwhelms the Coulombic attractions, then the molecules separate and exist as gas vapor. So basically you have a battle going on here between the motion, the energy in the molecules, and there's a natural attraction between molecules. We know that polar molecules have attractions to each other. The study of gas laws treats atoms, molecules, or ions in the gas state as though they're little balls. We don't care about protons or neutrons or electrons or SPDF subshells or sigma bonds or pi bonds. All we care about is they're these little balls flying through space that sometimes collide with each other or collide with the side of a container. Since the gas can be either atom, molecule, or ion, we use the generic term particle. Gas particles don't randomly change direction as they appear to be doing here. You must imagine that these particles are changing direction because they are encountering other particles that you can't see or the sides of a container. This gives gas particles their apparent random motion. Heating and cooling can also cause particles to change direction. Gases can take part in chemical reactions. For example, water is made out of hydrogen gas and oxygen gas to give water vapor. In this unit, we are only interested in how gas particles behave due to 4 factors: the pressure, the temperature, the volume, and the number of particles measured in moles. Pressure is the amount of force per unit area. The pressure of a gas can be thought of as the frequency with which gas particles hit the side of a container. So that's the way we're going to think of it. How many times does it hit the side of a container? If it increases, then that means the pressure has increased. The unit of measurement for gas law variables are: temperature is measured in Kelvin, volume in liters, moles in number of moles, and pressure has 5 different units of measure. One is atmospheres, the second is pascals, 3 is kilopascals, 4 is torr, and 5 is millimeters of mercury, symbolized mmHg. The one we're going to use the most is atmospheres. Basically, the pressure that you feel right now at sea level in this room is about 1 atmosphere. So 1 atmosphere is the normal air pressure at sea level where we are. The following are the conversions between the units for pressure. So 1 atmosphere equals 760 millimeters of mercury, equals 760 torr, equals 101,325 pascals, equals approximately 101.3 kilopascals. In the same way you made conversions between grams and moles, you can make conversions between any 2 of the measures above. Why there are 5 different units of pressure is something you don't need to understand. Just know how to convert between them. So here are some examples. There you see the equivalencies. They're all one big equivalency. So here's some examples. How many kilopascals in 2.3 atmospheres? So we start with 2.3 atmospheres. We see the conversion up above between atmospheres and kilopascals is 1 atmosphere equals 101.3 kilopascals. We can ignore the other 3. We don't care about them. And if you do the math, atmospheres cancels, and you end up with 233 kilopascals. How many millimeters of mercury in 105 atmospheres? So you start with 105 atmospheres, you go up above and you see that there's 760 millimeters of mercury equals 1 atmosphere. So we go ahead and make the conversion factor, we cancel atmospheres, and that gives us 798 millimeters of mercury. Finally, how many torr is 98,600 Pascal? Go up above, you see 760 torr equals 101,325 Pascal. So you start with 98,600 Pascal. You create a conversion factor, Pascals cancel, and you end up with 739 torr. Temperature is the average kinetic energy of molecules. Remember, kinetic energy is the energy of motion. Something has to be moving to have kinetic energy. The faster it's moving, the greater the kinetic energy. So this translates to meaning that higher temperature increases the speed of the molecules. Okay? Higher temperature increases kinetic energy, which is what it is, and that means it increases the speed of the molecules. So that would be, if you heat up that molecule, that hydrogen molecule, then it starts to do this. Temperature is the average kinetic energy of gas particles. Kinetic energy is given by the formula. You may have had this in physics. Kinetic energy equals 1/2 mass times velocity squared. So you can see from that formula, if you keep the mass the same, if it's the same atom or molecule, you don't change that, then as you increase kinetic energy, velocity increases. So we're going to say m is mass, v is velocity, and by increasing the temperature, we increase the average kinetic energy of the particles. Since the mass of the particle remains constant, then increasing the kinetic energy increases the velocity of the particle. Okay, now temperature scales. You've probably been introduced to these before. The scale we use here in the United States in everyday usage is Fahrenheit. For example, people will say it's 70 degrees outside. That's the Fahrenheit scale. We do not ever use that in science. There are two that we use in science. Centigrade, which is used in most of the rest of the world, and that deals from that scale is based on the idea that the freezing point of water is 0 degrees, the boiling point of water is 100 degrees, and therefore you break that division into 100 equal intervals, and that would be a degree centigrade. Okay? There's the Kelvin scale, which is the one scientists like to use because it actually references absolute zero. In other words, 0 on the Kelvin scale is the absolute lowest temperature you can have in the universe. There's nothing lower than 0 on the Kelvin scale. Now you notice the distance between the freezing point of water on the Kelvin scale, which is 273, and the boiling point, which is 373, is also 100 degrees. So the only difference between the two scales is what they decide to call 0. The centigrade scale calls the freezing point of water 0, but there's much lower temperatures than that, so you can go all the way down to negative 273. The Kelvin scale is a scale scientists want that says what is really 0. What is a number you cannot go below? It's the absolute coldest you could be in the universe. That's 0. And so it also uses the same measure of degree going up. It's 100 degrees between the freezing point of water and the boiling point of water. So if you need to convert, it's a very simple conversion. To get to Kelvin, you take the centigrade and you add 273. To get to centigrade from Kelvin, you take the Kelvin and you subtract 273. A lot of the formulas we use will be in Kelvin, and particularly one called the ideal gas law, and therefore if you're given the temperature in centigrade, you'll have to convert to Kelvin. Okay, so here's some simple conversions. Convert 25 degrees centigrade to Kelvin. So 25 plus 273 is 298 Kelvin. By the way, you're not supposed to say degrees Kelvin. You're just supposed to say kelvins. So 25 degrees centigrade, 298 kelvins. Negative 35 degrees centigrade is negative 35 plus 273 gives you 238 kelvins. 313 kelvins minus 273 is 40 degrees centigrade, and 260 kelvins, you subtract 273 from that and you get minus 13 degrees centigrade. Volume is the amount of space an object occupies in 3 dimensions. So right there, you see a balloon, and it can get bigger or smaller. So in some cases, the volume can change, such as a balloon. In other cases, the volume can be fixed, such as a glass or metal container. Volume is measured in liters. Often in chemistry, volumes are measured in milliliters, and there were 1,000 milliliters equals 1 liter, so we've seen that conversion before. So example, convert 467 milliliters to liters. So 467 milliliters times 1 liter over 1,000 milliliters, one of our standard conversions, equals 0.467 liters. Here's an important volume relationship between centimeters and liters. We've learned this one before, but we hardly ever use it. 1 cubic centimeter equals 1 milliliter. Generally, cubic centimeters are used for solids, and milliliters are used for liquids. Okay, so that concludes our introduction to gases and the units of measure that are used for them.